But he just requested this in 2.343. Let me see what that is. Yeah, that's a little funny. I probably didn't talk like this too well. They tell me the limit of some function as x approaches c. This is listen, it's some abstract function and it's some abstract c. I mean, nothing specific here. But they tell me the answer is 4 is what they tell me. So, whatever. It's very abstract. But then they ask this question. What's the limit of this function? What's the limit of this function cubed as x approaches c? And can you guess? I mean, we don't know the function. We don't know where we're going. This is very abstract kind of problem. But if the limit of this function is 4, if that function was cubed, and by the way, you know how you usually get that 4? What is the step for doing a limit? You plug that number in, and you get a 4. Well, I guess I would sort of plug that number in and get a 4, but then I would cube it. So I think the answer is 64. I mean, it was an abstract, strange question, but kind of easy and logical in a way, but kind of weird. I mean, anyway, if that limit's 4, this limit is 4 cubed, I guess. I mean, what's the next? Oh, yeah. So that, yeah, same idea. So it's the idea of kind of plugging it in. The next one is the limit of the square root of f of x as x approaches c. Again, if this is a 4, we got that 4 by plugging in a c and getting the answer 4, I guess. So if you do that here, I think you would get a 4, but it'd be square rooted, so you get a 2. Right. So did that help?
How'd you get a 2 again?
Well, because this is a 4, then that's going to be, when I plug this in, that'll be a 4. But it has a square root on it now, so the square root of 4 is 2. Yeah. So anyway, I might not do any more of those. C and D, they're all similar now that you got the idea. What else did you have? You said you had a couple of them? What else?
55. I don't get it.
55? Okay, that's classic. Check this out. 55 he's asking about. You might see this today. I think he's in 2.3, right? Yeah, still in 2.3. X squared plus x minus 6, x squared minus 9. X squared plus x minus 6, x squared minus 9. Is that what that was? The limit as x goes to -3. Thank you very much. All right, cool. Step 1 of doing a limit. Plug it in, see what you get. All right, I'm going to plug in a -3. I'm good at this. That's a 9 minus 3 minus 6. I think that's a 0. I plug a -3 in there and I get 0. 9 minus 9 is 0. So I got this 0 over 0 situation. Please, I've tried to teach you, don't stop here. This is where you need to start doing something. When you have 0 over 0, usually you can fix that somehow. And there's a lot of algebraic techniques, but the most common one here is factoring and canceling the bad factor. I mean, something's giving us a 0 over 0. I wish I could cancel that bad factor. So this is about factoring. And if you're good at factoring, this is an easy problem. If you hate factoring, good luck. I mean, I could try to remind you how to factor, but it's factoring. It's the denominator is the difference of 2 squares. That's a classic factoring there. The numerator is something, maybe 3 and 2, maybe 3 and 2. How about an x plus 3 and an x minus 2? Because that'll be -6, and that'll be a positive x. Yeah, that's how you do factoring. Anyway, now I can cancel that which is kind of the bad guy. So you can sort of tell now that it's factored, that's the part that's giving you the 0 over 0. And then now that it's canceled away, you plug -3 into what's left and you get an answer. I mean, now that it's canceled away, now you do the limit again, and you get -5 over -6. A -5 over a -6 is 5/6. We did that limit. That's cool. It started off being a 0 over 0. Oh no, what the hell? That's easy. You factor, you cancel the bad factor, and it works out. It's 5/6 actually. I could have investigated a graph and zoomed in on a graph and tried to get this answer. I mean, it's better to do these problems analytically. I mean, you can just get the answer. You don't have to waste time zooming in on a graph. Even if you zoomed in on a graph, you might not get 5/6. You know what I'm saying? So, yes, ma'am.
Are most problems like this when it comes down to the factoring and you get out the bad factor? I mean, is that basically telling you when you're going to plug in the limit when you cancel those bad factors?
I mean, that's a classic limit problem. You start by plugging it in, you get 0 over 0, and you have to fix it. There's several ways to fix it. We talked about factoring is one way to fix it. There was some problems where we multiplied by the conjugate. You know, I haven't done too many of these homework with you, but I did introduce you to 1 or 2 of these problems. And by the way, when would you multiply by the conjugate? When you see that square root thing, it's usually like 2 terms actually. Like when you got something like 3 plus the square root of x minus 5. I mean, that is some strange thing. Then you fix it usually by multiplying by his conjugate. What is his conjugate? 3 minus the square root. Right. So that's, I mean, that's a little nastier, right? The factoring's easier. This is a little worse. You know, maybe we should do one of those. And then there's this. Sometimes you have complex fractions, and you should get a common denominator. I believe I've done 1 of those or 2 of those. Sometimes getting a common denominator and simplifying your fraction helps. So those are kind of algebraic techniques that usually help you fix this. There's other options. There was some special theorems. You know, there was that special trig theorem about the limit of sine x over x as x goes to 0. When you try this, it's 0 over 0. But there was a special theorem that said this is a 1. And so we just kind of memorize that and use that when necessary. But then there's similar problems involving that anyway, you're right, there's all this stuff's in the homework. I don't know what you've been doing. We had that kind of that long break, and then Wednesday I jumped into a new topic, you know, continuity, and which I'd like to get back to today. But it's good to jump back in 2.3 and do a little homework. This is your quiz has these kind of questions on there. Any more from 2.3? 75. See, that's a trig problem.
Can you do 78 too?
Perhaps, yes. Yeah. Let's see what we got here. So he just said 75, which is the limit as x goes to pi over 2, cosine x over cotangent x. Wow. X goes to pi over 2, cosine x over cotangent x. So that's a problem. Now, it involves some trig. A few minutes ago, I highlighted this as a useful piece of information, but looking at that problem, I kind of don't think this is going to help me. I mean, this is for sine. This is for sine x over x. I don't really see that going on over there, but maybe I'm wrong. Maybe it'll evolve into that. Anyway, what's step 1 though? Before I go crazy, I plug it in. Maybe I get an answer. You know, if I plug in a pi over 2 to the cosine? You know, I don't know how much trig I need to remind you of. Pi over 2 is 90 degrees, and the cosine of 90 degrees is 0. So that's a 0. The cotangent of 90 degrees, boy, I'm not too good at that. Tangent of 90 is undefined. So I think the cotangent is the reciprocal of undefined. Do you know what the reciprocal of undefined is? 0, I think.
Yeah.
That's kind of a weird way to talk, but I think that's a 0.
So cotangent.
There's a lot of ways. You can't even do cotangent on your calculator, can you? I mean, there ain't no cotangent button. There ain't no cotangent button. But if you're supposed to know that cotangent is the reciprocal of tangent, so you could do, if you're trying to use your, you could do 1 over tangent of 90 degrees, or pi over 2. And I believe that'll tell you 0. I hope. If you're trying to use it. Well, tangent is undefined, but 1 over tangent is 0. I don't know if your calculator's smart enough to know that or not. It should be.
I didn't get that. I'm in degree mode.
Well, then you should have typed in 90.
Oh, yeah, I didn't.
And you typed in the tangent of 90?
That's what I got.
Let me see what you typed in.
Okay. 1 divided by 10, 90.
Yeah. Ah. Go to go-to. Go to go-to. I want to see something. That's interesting.
It's in degree mode.
Yes.
And you are in degree mode? Go to mode. Yeah, you're in degree mode. Yeah, that's undefined. Well, that didn't help. What about this? Did you know that cotangent is cosine over sine? So it's cosine of pi over 2 over sine of pi over 2. This helps.
Yeah.
Because the cosine is a 0 and the sine is a 1. 0 over 1 is not weird or undefined. 0 over 1 is 0. So maybe that helped convince me. But I was struggling with that. What did I say? The reciprocal of undefined is 0. That's sort of true, but it's kind of weird. And the calculator didn't follow that idea.
Because of a tangent being 1 over 0.
Yeah. Anyway, it's 0 over 0. So, fix it. I think maybe I'll use this idea that cotangent is cosine over sine. Hang on a second. So this is cosine. This cotangent is cosine over sine. What do you see? Once you start getting fractions over fractions, you're making yourself complex fractions is what you call that. And it'd probably be smart to invert and multiply, right? Flip this up and multiply by the reciprocal, right? The way you clean up complex fractions is I'm going to flip this up and multiply by sine over cosine. Well, that's sweet. The cosines cancel. This whole thing just turned into a sine function. Did you follow that?
Yeah.
Cotangent's cosine over sine. You flip it up, it's sine over cosine. The cosines cancel. You're left with sine. What's the limit as x approaches pi over 2? You plug in pi over 2 and you do the sine of 90 degrees. Everybody knows it's 1. Maybe not everybody, but it's 1. The calculator helps me with that. You guys all right? That was a good one. I mean, it's kind of a good one, but I used a basic trig identity to clean this up. That's what and so it helps to know some basic trig identities like that.
So when you flip the reciprocal to sine over cosine, what's canceled?
The cosines cancel.
All the cosine?
See, I'm doing this thing where I got like a fraction over a fraction.
Right.
And so what do? You
Invert multiple.
you bring him up and you multiply by his reciprocal. So you multiply by 8/5.
Okay.
And then I did some canceling if I could. So that's what I did with this. What was this? This was this was a cosine over 1. That's what this was. Divided by a cosine over sine. So when I flipped it up, I'm multiplying by a sine over cosine.
Right.
Then it canceled, and it left me with this. This, using this identity, turned into this. Right. She said 78. 78 is, yeah, let's see, 4 e to the 2x minus 1, e to the x minus 1. 4 e to the 2x minus 1, and then e to the x minus 1, and then take the limit as x goes to 0. Yeah, this is kind of fun. Yeah, this is good. It's really not that bad. But sometimes students have a little, students have a little weakness when it comes to trig sometimes, and sometimes they're a little weak with e functions. Anyway, the more you work with them, the better you might get. I like e functions myself. Anyway, step 1, plug in a 0, see what happens. E to the 0 is a 1. Anything to the 0 is a 1. That's a true old exponent rule. Anything to the 0 power is 1. So that's 1 minus 1, which is a 0. Up there you get e to the 0, which is a 1 minus 1. That's a 0. So it's 0 over 0 again. Maybe it needs fixing. It involves e functions, so it might be a little strange to you, but I see it pretty easy. Do you know what to do? Factor. Yeah. Good. See, that e to the 2x, should be thought of as e to the x times e to the x. What do you do with e to the x times e to the x? You add exponents, and you get e to the 2x. Right. Right, you can either think of, e to the 2x. Some students, watch, it's e to the x times e to the x. That totally makes sense, right, you guys? Because you add exponents. Or you can think of it as e to the x squared, which is, of course, what that is. Then you're multiplying exponents, but same thing. So you're saying that this numerator is the difference of two squares and it factors, right? What this is it is an e to the x minus 1 and an e to the x plus 1. It's the difference of two perfect squares and it factors. The denominator is this, and I think what we can do now is cancel that, what I've been calling that bad factor kind of. We cancel that. Don't forget, you're still trying to do a limit as x goes to 0, but I bet you now that you canceled that, you can do this limit. You plug it in. You get e to the 0, which is 1. 1 plus 1 is 2. 2 times 4 is 8. It's cool. That was a good one. Yes, ma'am?
Can you number 91?
91.
I like you should do 93.
Yeah, 93 is worse, and 92 is worse, and 94 is worse. 91's not that bad, but it... Didn't I do, what did I think I did one of these. I like all these questions. I appreciate it, you guys. But can I modify your question? Okay. I'm going to modify your question. So I'm going to do 93. What's the function? And then they want me to do this. And they want me to do this. I mean, this is, right? They want me to do that. They want me to do that, and they give me 91, 92, 93, 94. They give me 4 different functions. It's 4 different problems. Anyway, so every time you got a new function, but this is a classic thing. I mean, listen, you guys, I'd like to talk more about this, but maybe I won't do it right this minute. But this is what 3.1 is all about. 3.1 is all about this guy. And maybe I sort of explained it a little once. It's... You know, this is a y value. When you plug something in a function, isn't this a y value? And that's a y value. And when you subtract 2 y values, it's like a change in y.
Right.
And then that's a change in x. So it's kind of like a slope.
Right.
All right, hold on, listen. But a slope is usually, you have 2 points. You have 2 x's and 2 y's, and you're getting a slope. But what I'm doing, what this problem is doing, it's like a slope, 2 y's, 2 x's. It's like a slope, but then check this out. You're doing the limit as that change in x goes to 0. So those 2 points, are getting closer and closer together because the change in x is going to 0. Are you listening? The change in x is going to 0. Those 2 points are getting closer and closer together when you do this limit. And you end up really getting the slope at 1 point, or the slope of a tangent line. That was quick, but that was 3.1. That's called the derivative. That's half of calculus. But anyway, I'm not really there yet. But this is an important limit, and we shouldn't do these problems. And we'll do more of them if I ease into 3.1 next week. We'll do more of these. And they're kind of a pain.
Yeah.
They're hard. I mean, they're kind of
Messy.
they're messy and long, right? But we got to do a few. So, what I find students have an issue with is just reading it and understanding what to do. So I'm going to help you here. What this says is, please go to your function and plug in an x plus delta x. So I go to my function and I plug in an x plus delta x. So that was me going to my function and plugging in an x plus delta x. You with me?
Yes, okay.
And so I just did what that said to do. Please plug in an x plus delta x into your function. Okay, I did. Minus the function itself, which is just the function itself. Okay? So the function with an x plus delta x in it, minus the function itself, all over delta x. And now try to do the limit as delta x goes to 0. And maybe you can already see, I mean, I don't really want to go through this, but that's a 0 in your denominator. If you plug it in there, you get a 0 in your numerator. This needs fixing. This needs fixing before we can do it, right? Any suggestions on how to fix it?
Common denominator.
Good. I've got fractions in fractions. I should get a common denominator in my numerator. My numerator needs a common denominator. You with me? So that's what I need to do. And so, I don't know. So then I worry about students because they don't, I don't know. They might not understand common denominators too well. So hang on. In that numerator, I'm going to get a common denominator. What do you think the common denominator is of that numerator? That times that. I mean, those are two different denominators, and the common denominator is that times that. So the common denominator is x plus delta x plus 3 multiplied by x plus 3. That's the common denominator of those two things.
Right.
Now, to adjust the numerators, what do? You multiply him by what he needs. What does he need? Oh, he needs the x plus 3. You multiply him by x plus 3 minus, what do you multiply him by?
X plus delta
X plus delta x plus 3. I mean, that's how you get a common denominator, in case you forgot. And there we go. Now, this is going to be beautiful, you guys. You're home free now. This is all over delta x. And it might be cool to think of that as a delta x over 1, because I think I'm going to flip it up and get it all into one fraction. It's like a fraction over a fraction. It's like a fraction over a fraction. I want to flip it up and make it one fraction. I want to distribute that negative sign up there. This is going to be beautiful. This is going to be beautiful. It takes some writing. It takes some writing. You can't do it all in your head. You got to write it out. Hold on a second. What am I doing? Hold on. I was trying to do some stuff in my head. Hang on. Let me just, okay. So this denominator is this denominator, x plus delta x plus 3, x plus 3. What about, so if I distribute that negative sign, that'll be a negative x, a negative delta x, and a negative 3. So the x will cancel with the negative x. The 3 will cancel with the negative 3. And I'm left with a negative delta x.
And a delta x in the bottom.
You guys okay? This is just distributing a negative sign. Okay, that's all that is. And those terms canceled. I'm left with this. Now this is over delta x over 1. It's over that. I want to flip that up and multiply by his reciprocal 1 over delta x. I just flipped him up. Multiplied by the reciprocal. This is so awesome. Now the delta x cancels. I mean, it depends on your definition of awesome, but this is awesome. I'm left with negative 1. I mean, that was the key, dude. I had to get that delta x to cancel. That delta x is what's going to 0. That delta x is giving me the 0 over 0. Now it's fixed, dude. I canceled the delta x's. This is awesome. It's done. It's fixed. I've got this. This is sort of my answer. Now hang on. It's sort of my answer. I still got one thing I should do. Take the limit as delta x goes to 0, which means plug in a 0 for this delta x. And we are finished. We have this answer now. -1 over x plus 3 times x plus 3. X plus 3 squared, you could say. Yes.
So, in the denominator, x plus 3 squared. How'd you get that again?
Well, okay, I just let him go to 0. So I have an x plus 3 times an x plus 3.
Okay.
And I don't need to FOIL it out. It's x plus 3 times x plus 3. I don't have to FOIL it out. There it is.
This was after you plugged in.
After I plugged in, and after he goes to 0. When I do the limit, he goes to 0, and what's the answer? Right.
Alright.
And there is no more limit. I mean, we've done the limit. Don't write the limit again. We've done the limit, and there's the answer.
One more question on that.
Sure.
When you canceled out the delta x's, right?
Yeah.
Why does it turn out a -1? Because you canceled out the negative delta x and delta x. Would it be positive?
Well, I don't know. I don't know. Listen, it's kind of like this. If I just had -3 over 3, they cancel and they leave me with -1.
You're canceling the delta x's, not the negative.
I'm canceling the delta x's, not the negative
So
sign.
you can't have a negative nothing, so it becomes
So it's
-1.
-1 times 1.
I mean, if you cancel a 4 with a 4, that's a 1. But if you cancel right, I'm left with the negative sign. I'm left with a -1.
Just do the 3.
Hey, just listen to me a second, all right? Like I said, I kind of wanted to go into 3.1, and this problem is a 3.1 problem, but I haven't told you all the details yet. I mean, it was in 2.3 actually, but it's a 3.1 problem, and I tried to tell you the details. I tried to tell you, what did I try to tell you? That this is a slope. But it's a slope when the change in x goes to 0, so it's kind of like the slope at one point. Is that what I tried to tell you?
Yeah.
Which is, a phrase for that is the slope of the tangent line. And that's what this is. Now look at this. I'm saying that's a slope. And you might get a little pissed off at, I don't know. You might think all through your history, slope has been a number. Slope is 5. The slope is 7/12. The slope is a number. Well, all of a sudden in calculus, the slope is a function. The slope changes because we're talking about the slope along a curve, and we're talking about the slope of the tangent line. And if you're at that x, then it's got a certain slope. But if you move over to a different point, you've got a different slope. If you move here, you've got a different slope. I mean, the new concept in calculus is that the slope of a tangent line along a curve is a changing slope. And so the slope is a function itself. It changes with x. So the slope is its own function. And it's called the derivative of the original function. The original function was this. And we just found a formula for the slope at any point. We found a formula for the slope at any point. The slope of the tangent line at any point. Which is amazing. You might not think it's that amazing. It's amazing.
Do you think the derivative of the negative equals positive? Because the original
Don't. This is the slope of the tangent line. The tangent line, if it's slanting that way, has a positive slope. If it's slanting that way, has a negative slope. The slope could be positive or negative, or it depends. So the slope can be positive or negative. I don't know. this wasn't the full speech, but anyway, it's good. It's a good preview there of 3.1. What else? Any more homework requests? 2.3? 2.4? Let me go to 2.4 because that could show up on the quiz today. That was kind of a new concept. We were looking at some one-sided limits, and then we were looking at the concept of continuity. It's kind of funny. These one-sided limits are kind of funny sometimes. Look at this one. The limit as x approaches 2, 1 over x plus 2. Now look, that's one question. Here's a different question. The limit as x approaches 2 from the left of the same function. And then here's the third question. The limit as x approaches 2 from the right. That's what these little notation means, of this same function. Now this is real easy. I need a quick 1-2 minute break, so I'm going to come right back. I'm just going to hit pause on this.